Hi, everyone. This is Dan Barry in Silver Spring, and welcome to the October MAPP webinar. Thanks, everybody, for joining. Today's topic is seasonal prediction, achievements, and new frontiers, and we have three speakers. We're going to hear first from Ben Kirtman from the University of Miami. Ben's going to talk about the North American Multi-Model Ensemble. This is a major project that's funded by the MAPP program in the area of seasonal prediction. The project recently underwent a committee review, and Ben may talk a little bit about that. It's now supported by NSF, DOE, and NASA, in addition to core support from NOAA from the MAPP program. And Ben is also the leader of the NOAA Climate Prediction Task Force. This is a group of investigators that are funded by the MAPP program, about 30 individuals, and they're doing research in various areas of prediction, anywhere from subseasonal out to decadal prediction. And this task force has hosted a number of webinars recently. A couple of weeks ago, they hosted a webinar on the NAO and looking at the NAO as a source of predictability and prediction skill, and that's archived on our webinar website if you'd like to see the recording or any of the slides from that. And they also hosted a pretty novel virtual workshop about a month ago, entirely online, and had about a dozen speakers over the course of 2 days. And it was on the topic of bias correction for predictions. And those recordings and slides are also available on the MAPP website on the Climate Prediction Task Force page. Our next speaker is Eric Ghigliardi, from L'Océan Institut Pierre Simon Laplace and NCAS Climate at the University of Reading. And he's going to talk a bit about ENSO in the context of seasonal prediction, and ENSO, of course, being a major source of seasonal prediction skill. And Eric does leading work characterizing ENSO performance in climate models, was involved in CMIP-5 and has a number of papers comparing the CMIP-3 and CMIP-5 models, for example. If you're looking at the screen, a couple of those images have gone by. And then the third speaker will be Lisa Goddard from Columbia University. She's going to talk a little bit more expansively about some future directions and research opportunities for prediction, areas that could be explored by the research community. Lisa's worked extensively on seasonal to decadal prediction, and those are our three speakers. So I'd like to also mention that this particular webinar is co-sponsored by US CLIVAR. So thanks to Mike Patterson and Kristen Uhlenbrock for joining in. And I'll mention that each of the three speakers are well involved in US CLIVAR activities, both on prediction and ENSO activities that are organized by CLIVAR. So the format, we'll have the three talks. After each talk, we'll have some time for questions. The way that we do questions on these webinars is to ask people to use the raise hand feature, which is available in the participant list. There's a logo at the bottom of the participant list that looks like a hand. If you click that, we'll see that you have a question, and then we can unmute your line and you can ask the question and discuss with the speakers. So without further ado, I'll switch it over to Ben. Ben, are you on the line?
Yeah, I'm here.
Great. Okay, Ben, I'm going to transfer control over to your computer.
So hopefully you can see that.
Yeah, your screen is up, your slides are up. Looks good. So whenever you're ready, take it away. Thanks, Ben.
Okay. So we should start. So, just in case I run out of time, I just wanted to highlight some of the key accomplishments of the NMME project that we had reviewed September 5th, I believe the review was. And so just just trying to touch on some of these key points throughout the talk, with perhaps a little bit more emphasis on the introduction of CCSM4 in the NMME system. So we've introduced throughout the lifetime of the NMME, or at least phase 2 of the project, we've introduced 4 new modeling systems. We consider that to be a major accomplishment. And so now the real-time forecasts include over 100 Ensemble members. We've increased the real-time monthly data to 8 variables, and those are available through the IRI. The CPC website produces about 2,500 figures each month that highlight both skill assessments and actual forecasts. That's 2,500 figures every month, so it's quite a major undertaking. And then, of course, one of the things that we're most proud of, but also one of the things that we're really working very, very hard on, and that October deadline has slipped a little bit, but it is the most comprehensive seasonal prediction data set that's being made available. And it's one of the key aspects of that data set that I want to emphasize is it has a retrospective forecast data set and a real-time forecast data set, and those two things are consistent. So the real-time forecast and the retrospective forecast are done in the same way, and that's something we feel is very important also. As part of the project, we've certainly demonstrated the diversity of models is enhancing skill, and I'll show a result or two for that. We've tested, or we've begun testing a subseasonal multi-model protocol, and I'm not going to have time to report on that. And hopefully I will have time to report on just one particular highlight of prediction and predictability research. And I want to emphasize that there's a large number of prediction and predictability papers that are coming out using the NMME data. In fact, I have 4 papers in my inbox that I have to review, all of which use the NMME data in submissions to top journals. So I'm very excited about that. So just some of the things I'm going to highlight here, just underscoring the CCSM-4 effort that became real time on a regular basis in July. I do want to spend a moment in sort of quantifying the NMME benefit, this idea that the notion that really model diversity really is leading to enhanced skill, and then again those prediction and predictability results. So just a quick look. This is a demonstration of the systematic error in the Nino 3-4 region. The blue is CCSM-4, the red is CCSM-3 as marked. The black curve is the observational estimates, and so you can see the initialization in CCSM-4, both due to model improvement, but also better initial conditions, which I'll talk a little bit more about later. Definitely has a much smaller bias, although you do see this tendency for a semi-annual signal that's sort of coming up in CCSM-4 that you really didn't see in CCSM-3, but you also don't see that cold catastrophe, so we're quite pleased with that. And that, NCAR, the NCAR development process really does deserve a big pat on the back for that. That's nothing we've done. That's really the model development efforts. Just taking a quick look at the usual statistics. I'm going to emphasize mostly deterministic statistics today, but we've done a whole suite of probabilistic statistics, pretty much showing similar conclusions. The panel that you're seeing here is the left 2 panels are from CCSM-3. These are all January starts. These are verifying in the top in January, February, March, and then verifying in the bottom in June, July, August. And then the right panel, top panels are for CCSM-4. And you can see pretty clearly that there's much more reds, that the correlation coefficient has gone up quite a bit overall. I'm going to show you some difference maps based on the Z statistic in just a second, and then you can see the skill for JJA. Of course, the skill goes down in part due to lead time, but also in part due to less predictability in the summer season. This is showing the difference in the correlation as a Z statistic. So just to give you an idea where those correlations are statistically significantly better. And one thing to note, right at the equator, you can see that CCSM-3, right at the equator, is as good as, I would say, it is about comparable correlation coefficient as CCSM-4. It's really in sort of the extra tropical Pacific regions that we're seeing a benefit, and it is quite extensive in the Atlantic and in some places in the Pacific. We've actually started to do this, quantify where those improvements come from. And so here I'm showing you the correlation coefficient. This is 3-month lead, and the top panel is the CCSM-3 forecast system that we submit in real time and continue to submit in real time. And then the bottom panel is using CCSM-4 with the identical set of initial conditions. Okay, and so that's just initializing the ocean, so it's identical set of initial conditions. And so what we can argue, based on this figure, that the improvement here is due to model improvements. And we can push that a little bit further now. Now here, the top panel is showing that same correlation coefficient, but now this is now the using the improved, what we think are improved ocean initial states only in CCSM4. So this big bump over the bottom panel is both due to model improvement and what we believe is a better initial condition. So the improvement is the initial condition, maybe a better data assimilation system, maybe better data, maybe better quality control, and a better model also contributes to that. But we're just saying generically a better initial condition. Going a little bit further, one of the big criticisms, again, this figure is in the same format as the SST skill scores, same format. This figure is now looking at the 2-meter temperature verification, again, in terms of anomaly correlation. And one of the biggest criticisms of the CCSM3 forecast that we're submitting is we don't initialize the land and the atmosphere. And so you can see that these correlation skill scores are really quite low for CCSM3. And we're pleased to say that, you know, after a great deal of massaging, and Dan Polino worked very hard on this, and Min Du Hong worked very hard on this, developing a land and atmosphere initialization that could be plugged into CCSM4. Now you're seeing a much improved correlation coefficient over land areas. And just like before, we can actually try to quantify really very carefully how much of that forecast improvement is really coming from the land and atmosphere initialization. And so here I'm showing you differences in the correlation coefficient. So this is, again, that Z statistic. And in the top panel, I'm showing CCSM4 minus CCSM3 in that Z statistic with stippled regions showing statistical significance, where we have the full up ocean, land, atmosphere initialization in CCSM4. And so you can see improvement in the land correlation coefficient in that first month really quite clearly showing up. In the bottom panel, we show that same difference in the Z statistic, but here we're only initializing the ocean. So the initialization strategy with CCSM4 and CCSM3 is identical here, and so you're just looking at model differences. And so you can really see that the land initialization here is playing a major role, land and atmosphere. I can't eliminate atmosphere, of course, playing a major role in improving that 1-month forecast scale. Just moving on a little bit, one of the big challenges with the NMME project was to demonstrate that model diversity is really improving the forecast skill. And so there's questions of ensemble size versus model diversity. And Hugh Vandendoel and Emily Becker and their colleagues developed a nice technique for evaluating this, and I just want to show you a result or two and explain that and how that works. And one of the key elements is to actually form a mini NMME that does not include CFS, and so we can actually look at an ensemble size that's identical to the CFS ensemble size, but does not include CFS and has some model diversity to it. And so they've put together a nice set of tables. This is based on Breyer skill score, and I just want to focus on those 2 columns that I've highlighted with a black box around them to make it easy to look at. And in fact, we can just look at the red. Let's just look at the above normal. So this is a Breyer skill score based on above normal and below normal categorical forecasts. And the top is showing results for 2-meter temperature over the extratropical land areas only. So 23 north to 75 north. And so what you can see, if we just look at these numbers, the CFS 24 members, the above normal score is 0.01. It's positive, which means there's some skill. It's a small number, but it is positive. And then the mini NMME, that's 24 members that doesn't include CFS, that has a number of 0.03, and then the full NMME has a number of 0.06. So what we can safely conclude based on that picture, based on those three numbers, is that model diversity contributes, and indeed the increased ensemble size also contributes. And so you can actually argue that perhaps most of the improvement for 2-meter temperature over North America is due to ensemble size, but certainly a contribution from model diversity. Now, if we take a look at the lower table, this is the Breyer skill score for NINO 3.4. And again, let's just look at the stuff highlighted in the black box and just look at the three red numbers. And this talk is available, so you can look at all the other tables as you wish, all the other entries as you wish. And so the numbers go 0.39 for the 24-member CFS, 0.55 for the mini NMME, and 0.55 for the full NMME. So in this case, we can argue that all the improvement, that is, all the improvement is due to model diversity associated with the NMME. So we consider this a pretty compelling result. And of course, I should underscore that this is something that has been out there. People have understood that, but precisely how much is due to ensemble size and precisely how much is due to model diversity, it's nice to sort of quantify that separately. So this is a nice presentation of that result. I still have a little more time. Dan hasn't given me the hook yet, so I can try to cover some of the prediction and predictability results. And just real quickly, one of my students has been really interested in looking at differences in teleconnections associated with the diversity of El Nino events, this usual notion of Central Pacific versus East Pacific warm events. And so what you just, this figure up here is just showing you a time series of NINO 3.4, and she's highlighted the sort of the two poster children, if you will, for a Central Pacific event, 1995, and an East Pacific event, 1998, there for you. And the maps are simply the top two going across are Central Pacific rainfall maps and East Pacific rainfall maps, where she's just showing the sign of the anomaly. So green implies increased rainfall, and brown implies decreased rainfall, just the sign. And then the bottom two panels are, again, just the sign of 2-meter temperatures associated with Central Pacific and East Pacific events in general. These are composites, but she's highlighted the two poster children, but the maps are for composites of all the events. And so we did look pretty carefully at how well these various events are forecasted, and it just 95 and 98 are really good ones to look at, and Dan has given me the 2-minute hook, so this will be the last slide I show. The open circles, tiny colored circles, correspond to the 1995 case, and the closed filled-in circles correspond to 1998. The red or brown triangles, I can't tell that color, correspond to observations. And so you can see, if you look at the top left box at a half-month lead for seasonal mean, this is JFM. JFM, you get a clear, the models give you a nice clear separation between the 1995 case and the 1998 case. When you go to longer leads moving across, that becomes a little more blurred, and you can see that particularly for the 1998 case, you get a much bigger scatter compared to where the observations are sitting. But you do still see that contrast, east-west contrast, even though it's probably warmed up too much in the east and the structure is not quite right, but there is a distinctive east-west contrast in the forecast results. And again, you can see that in the rainfall. This is the good slide, but I'm basically out of time.
Talk about the slide. Talk about the slide.
Oh, okay. So so let's just look at the top two panels. What this is really showing you, if we look at the green curve, for example, the green line, the green dots, that's showing you southeast rainfall, and it's really showing you very clearly that if you take the top left, you're seeing a linear relationship between the amplitude of the tropical SST forcing and the rainfall response over the southeast U.S. for the East Pacific events. So basically using Nino 3 as an indicator of East Pacific events. And then if I go across to the right-hand panel, now you notice that the green line is flat, but the red or yellow line is now sloped. You're seeing a nice linear relationship between rainfall in the Northwest and the Northeast with Nino 4. So you can actually start to think about what your teleconnections would look like and how linear the relationship is between the response. And you get similar results because we really sort of think of the precip as more related to actual forcing. Bottom two panels show sort of a similar interpretation. So I'll conclude there, just showing you the accomplishments. I really do want to emphasize that it's a really team effort. A lot of the slides here that I showed were contributed by team members, and that there's a lot of good new prediction and predictability research that's emerging because we've come together as a community to really make this data set readily available. And this daily data that's now coming out from the NMME project, I think, is going to foster a whole bunch of new research in terms of understanding weather within climate. And I'll stop there. So thank you.
Great, thanks a lot, Ben. And I'm glad you threw that slide in. There's always so much good new stuff coming out of the NMME project. So again, as a reminder to everyone who's logged in virtually, the way to ask a question is to use the raise hand feature in the participant list. So just go into the participant list. At the bottom, there's a little hand diagram, and you click that. That'll let me know that you have a question. I can unmute your line, and then you can go ahead and ask your question. So please use that if you have a question for Ben or any of the other speakers as we move along. I haven't seen any hands raised yet. So, actually, wow, they're cascading right now. Okay. So I think Ray Errett was first. So Ray, I just unmuted your phone line. Are you there?
Yeah.
Okay, great. Go ahead.
Okay. Yeah. Ben, are you seeing a lot of papers looking at applications of NMME? I'm particularly interested in agriculture here, but I'm just curious if other people are trying it on the applied side.
A little bit. So I'm definitely seeing some stuff out of Eric Wood's group in terms of using that to drive hydrologic applications. But I'm also seeing, without giving away what I'm reviewing at the moment, I have a couple of papers that are actually looking at drought and agricultural applications in a couple of different areas. I've also seen the UF guys are really looking at that from their ag school and their water resources efforts. So I am starting to see some of that stuff, but it's not definitely not a coordinated effort. I would argue that individuals are attacking the data and confronting it, and but that's what I'm seeing so far.
Thanks.
Okay, thanks for the question, Ray. Second question is from Krista Peters-Ladard. Krista, are you on the line?
Yeah, I'm here.
Okay, great. Go ahead.
Okay. Hey, Ben, I'm curious about the land initialization. Obviously, it makes a huge difference in the 2-meter temperatures. What exactly was done for the land initialization?
So what we did is we took CFS R data, or CFSR data, and mapped that onto CCSM4 or CLM as best we could. So it's messy and ugly, and there are some things that we don't like, but we basically try to take what's coming out of CFSR and map that onto CLM. The nitty-gritty details I could give you, but that would take a half hour, all the nitty-gritty stuff. So
that's good. I mean, I think one of the key things about the CFSR is that they use observed precipitation to drive their GLDAS. So I'm assuming you were pulling the states out of their GLDAS system before they got transformed to C. Yes. Okay. All right. Thanks.
Okay. Thanks, Krista. So those are the two questions that we had so far, and I think in the interest of time we should move on. So Ben, thanks a lot for the talk and for answering these questions. Okay. So our next speaker is Eric Giliardi. Eric, are you on the line?
Yes, I am.
Okay, great. I'm going to transfer control over to your computer.
Okay. Right. Do you see the first slide?
No, not yet. So did you hit the share my desktop button?
Let's see. Right.
Okay. Great. Coming up right now.
Right. Let me know when you see it.
Looks good. Yeah, go ahead. Thanks, Eric.
Okay. So hi, everybody. Thank you for the invitation to join this webinar. So as you've seen from Ben's presentation, the quality of GCMs used for seasonal forecast is absolutely key. So what I will present you here is some work we've been doing over the last years to understand how ENSO is representing climate models and trying to go from the regular performance metrics or statistics, as I call it in the title, to more process-based metrics to understand if ENSO is represented right for the right reasons, and because sometimes it's for the wrong reasons. Right. So I will illustrate those basic statistics looking at the two last generations of GCM, so CMIP 3 and CMIP 5, and we'll see if there have been some improvements. Then I will speak briefly about the mean state in tropical Pacific, because even though we look a lot at anomalies, these anomalies develop on the mean state, and looking at what happens to this mean state in GCMs is really important. Then a brief part on ENSO in the warming climate. There's new and exciting results coming out, so I thought I'd share that for a minute or two. And then I will spend the last bits on the process-based evaluation of ENSO, and with a focus on the atmosphere processes. So basically, if the line gets dead, or if everybody's has to go, and this is basically the what will come out of this talk. I'm trying to show is that the mean state and ENSO statistics in CMIP are improving, and we have new robust information about ENSO in the future, especially in El Niño extremes. But the process-based performance is still an issue. We don't see any evolution from CMIP 2 to CMIP 5. Right, so this is the classical El Niño amplitude, with as measured as, for example, the standard deviation in Niño 3 of the SST. So you can see, I think I can use my mouse. So the observations are about 0.9, between 1.9 Celsius in standard deviation. And the blue dots are CMIP 3 generation, and the CMIP 5 are in red. At the bottom, you have all the modeling centers. So they're anonymous here, but if you go and look at that paper, you'll see all of them. So a few things to see here. First, the diversity of representation of El Niño in models has been reduced from CMIP 2 to CMIP 5. Now there are no more models that have either twice the amplitude or no more ENSO, like you would see, for example, for those extremes. So now the models are more or less around the observation. So that's good news. And of course, the question is, why is that? So there are two possible sources. First, the improved mean state, the improved models, are now tuned in the modeling development process. And as you'll see, I think the second answer is the right one. All right, moving to the frequency, another typical important metric. So on the left, you have the CMIP 3 spectra, and here you have the 2 to 7 year observed band, and the black solid curves with different styles or different observational products, and then the different simulations are in color, in thin lines. So you see for CMIP 3, you had models that had no ENSO whatsoever, okay? And also most of them had like a 2-year periodicity, so too high frequency. When we move to CMIP 5, this is much improved. Now all the models have an ENSO, which is good news. And you see a shift to low frequency as in observations. So we've tried to develop a spectral shape metric, but it's, so again, getting a metric for the spectra is difficult because it's not very robust. As, for example, Andrew Wittenberg's paper has shown, you need several hundred years to actually have a robust metric, because you can have centuries with very different properties from other centuries, and these are, pre-industrial runs for, I think there was 200 years. So what we've done is taken the ratio of the power in the 3 to 8 year band to the 1 to 3 year band to see basically if we're getting the right value as in observations. It's that black point here. And you see again for CMIP 5, a clear improvement in the diversity of model, although there are still errors. There are still models having like a ratio of 3 instead of ratio of 1.2. But that's giving a handle of how the model might be performing. But again, for this, we need long simulations. Right, this is the frequency. Now, I'm shifting to the mean state against which those anomalies develop. And this is the SST here along the equator for the observations in black, the CMIP3 in blue, and the CMIP5 in red. So the ensemble mean is in a solid line, and then the spread is represented by the shading. So, and this is the same thing for the zonal wind stress at the equator. So the good news is that the classical cold tongue error, is going basically the cold tongue extending too far west and opening the wormhole, is reduced by about 1/3 in the CMIP5, so that's nice. We still have 2 strong trade winds in the West Pacific, as seen here, especially in the central West Pacific. So again, here we have to be cautious because the observational reference, so we have a number of products here, and depending which one you take, it might give you a different answer. So that's another issue, is that sometimes what the reference is not clear for those even the last decade or so with new products. Right, so we have improvements in the cold tongue error, so that's good. The other important aspect is the seasonality of El Nino, which again builds on the mean annual cycle. So I won't go into how the models are performing the annual cycle, but this is the seasonality of El Nino, which has important implications for teleconnections and impacts. So you see here, again, the same code as before. So the observations are in black, and then the 2 families of models. So you'll see on average, the CMIP5 does a bit better job in capturing the spring, although it's too late, the spring relaxation and the winter maximum. But still, if you look at individual models, not many have that property. And it's a bit improved from CMIP3, but not that much. So this is still an area where models have to improve things. And again, you can devise a metric. I won't go into that for the sake of time. So what I forgot to mention in those metric plots, those squares with whiskers are the multi-model mean and the intermodal standard deviation. So you can compare both how the mean error is changing and how the models are spreading around that average. Right. Now, briefly, some new results that came out of a paper that was led by Wenju Chai that came out earlier this year, looking at ENSO in a warming climate, as you know, is a hot topic. And up to now, we're not really able to come up with any specific signal for the future. If you take the SST Nino 3, we don't really see any signal. And so here, what Chai al did is that they focused on the extreme El Ninos. And extreme El Ninos are interesting because they have the largest impact, and also they have a distinctive SST gradient signature and also precipitation, and this is how it was basically diagnosed. So on the left, you have a Hovmüller at the equator for moderate El Ninos, and so the green curve is the precipitation, and the purple curve is the eastern edge of the wormhole. And you see for extreme El Ninos on the right, so this is a composite from observations, basically the precipitation is going all the way, anomaly is going all the way to the east, so we have precipitation in the far eastern Pacific here, and that's how you can define this. So one way to relate, so you can relate the Nino 3 rainfall here to the Nino 3 SST, and you see how those 2 extremes of the observations stick out from the others. And the meridional, you can do the same thing with the rainfall and the meridional SST gradient, because basically if you get rid of your meridional SST gradient, reduce it, then the convection can move to the equator, and you have that thing. So now let's see what the models are doing. So if you take the CMIP3 and CMIP models that do have extreme El Ninos, not all have it. So you make a selection. There's about 15 models that can have those extreme, and it looks pretty good. I mean, when you compare the composite for both, you do see those models having a similar behavior, both for the moderate and the extreme. And when you look at the present-day climate, so this is the historical runs, and now, of course, you have many more points than for observation. That's the nice thing about those. You see that for the 20th century, and if you put a threshold at 5 millimeters per day, you have about 70% of extreme El Ninos compared to the others. And the striking result in this paper is that if you go to the RCP 8.5, you end up with 38% of extreme El Niños. So that's doubling of the frequency. And the reason for that is pretty simple. It's the fact that when you look at the mean climate change in those models, you see that the equator is warming more than the surrounding regions, so that your gradient, which acts to prevent convection to move either from the west or from the north into the East Pacific, is reduced. So in the future climate, this gradient is weaker, so it's easier to go in extreme El Nino. So this is both a statistical and physical robust result. Of course, it depends what exactly the mean state will do, but there's some papers explaining why it should warm more where the water is cold than other places. So that's really pointing to the fact that the process-based metric can tell us more about El Nino. And that moves us to the role of atmosphere during ENSO. So I won't go into all details of the theories, but basically the atmosphere feedback during El Nino, if you take, for example, the recharge of theater and do a linear stability analysis that's developed with that the Bjerknes index, the BJ index, you come up with a number of terms that will tell you about the stability of ENSO. And one of them is the negative heat flux feedback, so the alpha term here, both mostly the shortwave and the latent. And the other one is the Bjerknes feedback, the mu, which is a positive feedback that is playing a role in the ocean feedbacks. So you can look at these different atmosphere feedbacks in the CMIP 3 and CMIP 5 model of families and see if there's a change. So this is the Bjerknes feedback here, and again, all the centers and the different models. You don't see really any improvement from CMIP 3 to CMIP 5, maybe a reduction in the model diversity, but still too weak compared to what the observation is showing. You do see individual models doing okay, but no major global change. Same story for the heat flux feedback, which is usually also too weak, and basically you have an error compensation between the 2 week positive feedback and the 2 week negative feedback, so the two compensate to give you the right ENSO amplitude, but probably for the wrong reasons. And if you look at the contribution from the shortwave and the latent to that total alpha here, you see that the latent is not too bad. It's really the difference between the models coming from the shortwave feedback. Not surprisingly, this is basically where the models are having troubles with the clouds and the response to the low cloud property and the response to dynamics. And if you look more specifically at the shortwave heat flux, you see that some models, it should be about -7 watts per meter squared per Celsius. A lot of models happy to do positive feedback, so completely wrong sign. So this is an area where we need to progress. And here what is important is that there's no clear evolution from CMIP 2 to CMIP 5. That's why I was saying the improvement in CMIP 5 is that people are looking at the statistics and they discard models that are not doing ENSO, but we still have the same basic error compensations. Right, the source of alpha errors are basically coming from the two regimes we have in the Central and East Pacific, the convective regime, which has a negative alpha shortwave, and the subsidence regime where we have a positive, so that's the convective high cloud regime. This is the cold tongue low cloud regime. Both coexist in Nino 3, and the ability of the models to have the right value of each, the right geographical repartition, and a way of shifting from one to the other during El Nino is absolutely key to get the right value. So you see it's quite a lot to ask for GCMs. Right, now, another aspect is the nonlinearity of that alpha shortwave. Usually the theory is taking as a linear relationship, but it's not. We know that because of those two regimes, it's negative in basically the subsidence regime here, and positive in the convective regime. So sorry, this is Nino 3 anomalies, and this is the heat flux anomaly. So it's a mixed regime observations, and if you classify the models, you'll see that some are only going to be in the subsidence regime, some only in the convective regime. And if you look at the CMIP 3 and CMIP 5 models, there's about 1/3 of each. So that's a nice metric to look at. You can look at it in an AMIP model already, it will tell you a lot. And all the models that are in the trial I was showing are in the mixed regime. So you need the mixed regime to have the extreme El Ninos. Right. So, and now if you look at your mean states, not looking at just to which family you belong to, but to which regime you can reproduce, you can see that, so the observations are still at black line, the middle panel, and basically to make a long story short, only the mixed regime, which are here, the observations now are in green, and you can see in terms of slope, which is absolutely key to have the right slope, to have the right convection patterns, the right trade winds, the right upwelling. You see that only the mixed models have the correct slope compared to observation. The convective model have too shallow a slope, and the subsidence model have too sharp a slope. And again, this is showing that if to have the large El Nino amplitude, and if you measure that alpha nonlinearity, you only have the large one when you have a lot of nonlinearity. Right, so what that means is that basically those better heat flux feedback and ENSO also come with a better mean state. So working on the mean state is absolutely key in GCMs. All climate models know that, but even for the variability, it's really important. Right, so one last slide to talk about performance versus process-based metrics and see if we can find any relation between the two, which would be nice. So this table is basically showing for CMIP 3 and CMIP 5 all the different performance metrics in terms of amplitude, structure, spectrum, seasonality for the models. And the more, the normalized error, the more blue you are, the better you are off, and more red, the worse you're off. So we can make an ENSO score by averaging those, which is very, ad hoc. We don't know how to average metrics to give you an average metric. We have no physical base of doing this, because, as you know, that doesn't necessarily prevent people from trying to. And then you can do the same with the different atmosphere feedbacks here that I've shown, and again come up with it. So that might be helpful when you're developing a new version of the model to see how your model is performing compared to the previous version. But if you try to make any relation between here, the ENSO scores and the feedback score, you don't really see any relationship. And one reason is clearly that you need also the ocean feedbacks to have the full relationship between the different feedbacks and the ENSO score here. Right, so as a summary, we have a marginal improvement of ENSO statistics when going from CMIP 2 to CMIP 5. And basically, we have better mean state, we have less poor performing models, and a lot of the improvement of the multi-model means coming from that. Now groups check the ENSO statistics, and we will not keep a model that has no ENSO. So the improvement we're seeing is not necessarily because each individual model is improving. Using the rainfall as a proxy, as a function of the meridional velocity gradient, as a process-based metric, help us to understand what may happen to El Nino in the future. And this is the first time we have a robust result about ENSO in the future, showing a doubling of the number of extreme El Ninos in extreme. Well, the RCP 8.5 is a kind of an extreme scenario, but that's encouraging. Also, the poor modeling of ENSO feedback suggests that improvements are often results of error compensation. So that there's a little change from CMIP to CMIP 5. So that's really advocating for modeling groups to develop the model looking at those error compensations. And there are ways of doing this I haven't touched upon here. Like there are a few groups now have started that. We've done that at IPSL, and I know Andrew Wittenberg and EAL, and also people at NCEP are doing that as well, is to work in an initialized mode where you're going to let your model drift away from observations, take a hindcast from seasonal forecast, and by doing that, you're going to see how your model is going away from observation, and look at the time scale and the processes will inform you of where the error might come from, so you can get rid of your error compensations that might start this way. Right, so large errors come from shortwave heat flux feedback. Not surprisingly, the role of clouds, convection, large-scale circulation, and we've shown also the specific role of nonlinearities. It's really important if you want to have extreme El Ninos to have the nonlinearities working well in your model. And also there's evidence that improving the mean and annual cycle will also lead to process-based ENSO improvement, not only the statistics. Sometimes it will degrade your statistics, but you have better processes. All right, so I think in the interest of time, I'll stop here and take any question.
Great, thanks a lot, Eric. So we have time for probably one quick question. So anybody in the virtual world, if you raise your hand, I can unmute your line. You can ask the question. While we're waiting for that to happen, Ray and Krista, who asked questions earlier, you guys can put your hands down unless you have another question. I'll give it a few seconds. Are there any questions here in the room? Okay, I'm not seeing any hands going up, so I think we should move along. Eric, thanks a lot.
Okay, thank you all. Thank you very much.
Okay, final speaker is Lisa Goddard. Lisa, are you on the line? Hi, Lisa, are you there?
Yep.
Okay, great.
Can you hear me?
Yeah, we can hear you. So I'm transferring control over to your computer right now, and then just click the Share My Desktop button and bring your slides up and take it away.
Okay.
Yeah, it looks good. Thanks, Lisa.
All right, thank you. So I'm going to talk about some of these opportunities that I see both for making better predictions and also opportunities for this entire research community that's on the call and that we connect with. Like anything human, it's subjective, so my list of opportunities are going to be relative to the sorts of work that we're doing at IRI. But a lot of that really starts with seasonal forecasts, so the focus is going to be primarily on seasonal information. This is an example of a typical rainfall forecast. We have these sort of regional areas, 3-category forecasts, that if you knew nothing, you were in one of these white areas, your odds of being in below normal, near normal, or above normal distribution of the climate would be equal odds. So we're looking at a shift in the odds. So, for example, this yellow area is suggesting 40% probability for below normal. This is a very similar type of format that's used by the Climate Prediction Center as well. It looks a little bit different, but it's giving a similar type of information. And there are a few things with this. First of all, in the way that this is often viewed by, say, our program managers and the people that they have to talk to, there's a perception that we really haven't advanced, and what investments are important to make this information better. And I would actually argue that there have been a lot of improvements, a lot of important research that has gone into making this information better and more usable. The difficulty is that a lot of the metrics that are used to look at this information are just saying, okay, we have this brown blob. It doesn't really matter what probabilities we assign to it, but was it observed to be below normal in this area, and then either yes or no. And I think that perception, that way of viewing this information, is limiting us in our communication, both with the government that funds our work and the broader public. The other thing about these maps, and I'll go back to ours, so I'm just not up here to be criticizing Climate Prediction Center, people don't like these, especially the people that have to use them. It's very limiting. They don't know what is below normal. They're really not sure how to use this information. And so I really think that there are a lot of opportunities to go beyond this type of information. So again, in the subjective interest of my talk, the opportunities that I'd like to talk about, certainly there are more than this, are in the reliability as well as the sharpness of our forecasts, and I'll describe what that means, to extend the information content at the seasonal timescale to include subseasonal information as well, and then to actually use these in a real context, say sector-based, and I'll give one example of that. So starting with the issue of reliability and sharpness, for those of you that do forecasts on a regular basis, you'll be familiar with these graphs, but for those of you who aren't, these are actually from IRI's real-time forecasts. So this is not corrected hindcast or anything like that. These really are our forecasts from the 90s, which means that there have been evolutions in the system over time. Just a detail. What this graph is showing you is for a given category, that's the different colored lines, given the confidence with which you assign a forecast in that category, say an 80% likelihood, let's get something more conservative for rainfall, 60% probability of being above normal, you want, when you say that, for that to occur 60% of the time. So a reliable forecast system would be something that over time, over space, lies along this line so that your probabilities that you assign to some outcome really are very meaningful. So that's reliability, and it's a really, really important goal of forecasting systems, and especially if that forecast information is going to be used in a real context. The other thing is sharpness. So what's being shown down here is how frequently do we actually forecast any of these categories with what confidence. And so this, 1/3 likelihood is sort of the default. That's a climatology, and you can see that it's pretty infrequent to get these very confident forecast levels. That may be just the way that the climate system is in terms of what predictability we're actually able to mine. But I think it's also an important area to continue to pursue. Can we maintain the reliability while increasing our sharpness? That means increasing the confidence with which we assign a likelihood of a given outcome. So we absolutely want to do that. One of the important questions then is how do you determine the uncertainty? How do you make sure that the information that you provide really is meaningful? And I know, and as Dan mentioned, there was this whole virtual webinar on bias corrections of subseasonal to interannual predictions. So I'm going to show one or two slides. This is related to a project that we have and is in collaboration with University of Exeter. So the idea is that this is the potential mapping between the observations that you have to verify against and the set of forecasts with some mean and some standard deviation. So you might do a bias correction on the mean itself. This correcting the mean bias is a very standard, but you might have conditional bias as well. Do you just need to scale the variance of your forecast, or do you actually need to replace it with your known error on this mean? All of these are important questions, and what Phil Sansom has found in his research on this project, and is very consistent with our experience, is that actually the spread of the ensemble has limited information in a lot of places, and in a lot of places would do better just replacing it, knowing what the mean ensemble mean is of the forecast and replacing the uncertainty with the uncertainty in that mean over some set of hindcasts. And so what this graph is showing you is where it's red, that's where estimating the uncertainty by this mean squared error is actually a better estimate. It's more reliable. So that's, and I think that was an important discussion in this webinar was, what methods can you bring to the table when you're correcting information locally, which is where you have data, which may be where you're using the information. Something that we've also found, though, is that it's very important to consider the spatial errors in your forecasts as well. And so this is, I think, an opportunity for looking for that increased sharpness. So this is just an example. This is showing climatology of rainfall over Africa, and this is where the rainfall is the heaviest. And you can see that there's a spatial bias in the way that ITCZ comes across Africa. The main variability in this season is for that ITCZ to shift north and south. So in this case here, we're suggesting that this is a year when the ITCZ shifts north or shifts effectively parallel to its axis. The model's trying to do the right thing. It's trying to shift relatively northward parallel to its axis, as in the observations. But the reality is that due to that mean bias, the local agreement is going to only work in certain places. So where those two wet areas overlap, it's going to look like the model's doing pretty well. And where they don't, where the observations would say dry and the model would say wet, that's actually where you're going to end up with poor skill. And that's exactly what we see coming out of anomaly correlations in the model. So the idea is if you have these sorts of systematic biases, not just in the mean state, but in the variability as well, that should be taken into account. That's sort of a zero order correction that we want to make. And this is something that Tony talked about in the virtual workshop, that if we can do these sorts of spatial corrections first that then include some of those local calibrations, that can actually give us more confident, and at the same time still reliable information. And once we end up with reliable information, taking those probabilistic forecasts and moving them towards something that really gives information across the entire distribution, not just in these three categories, can be very useful. So this is an approach that IRI has been taking. It's something that actually the Climate Prediction Center had started some time ago, focused more on stations, but this is something that an extension of the probabilistic forecast that we've found very valuable for ourselves, but I think that there's still a lot of opportunity to improve the information that goes beneath these distributions. So the second is in terms of subseasonal information, and again, there's both characterization of variability within the season as well as predicting actually the subseasonal information. So this is sort of the iconic figure of this. Research was done about 10 years ago, and what it's showing is for 2 different years in India, the yields from these 2 years are dramatically different, even though the total rainfall is almost identical. So the seasonal forecast for rainfall might have been, let's say it was perfect, would have been the same in these 2 years, but the outcomes agriculturally would have been very dramatically different just because the way that the rainfall was delivered, much more smoothly, evenly in this year, while in this year's heavier rainfall events separated by long dry spells. So we want to be able to capture that. And actually there's a growing body of research that suggests that some of these characteristics might be more predictable than the seasonal total. This is actually from a statistical forecast showing the correlation between the forecast and observations. For the seasonal total, that's this graph here, the frequency of rainfall on across the season is more predictable. What's hard to predict is when it rains, how heavy is that rainfall? And so it's this uncertainty and the intensity that's sort of pulling down our seasonal total scale. But the predictions themselves will be very important because there certainly are events that impact society that people need to know, need to prepare when they're coming. They have very dramatic effects, not only on the people, but on our economies. And so there is this extremely important working group that's been developing on subseasonal to seasonal prediction that's joint between the World Climate Research Program and the World Weather Research Program. They have an implementation plan. They're putting together a database of hindcasts, and I really hope that someday, not too far in the future, that this will be like a subseasonal version of the NMME. I think that would be fantastic. In the interest of time, I'm not going to go through the extremes, but just to say that this is really an opportunity for improvements of models and uses of our models, because we know that between the observations and the models, GCMs are in most places, especially where it rains in extreme amounts, they're not capturing that wet tail of the distribution. And regional climate models that just are able to capture these high rainfall amounts are not really fixing the problem, because they're actually greatly distorting the observed distribution in order to accomplish this. So this might be one of those, as Eric says, right answers for the wrong reasons. And so I think that this is still an enormous challenge for modeling and our use of these imperfect models. Of course, to do any of these things, even to know what it is that we should be doing, we need observations. So those are pretty good in the US, in Europe, and in a few parts of the rest of the world. But in a lot of the developing countries where IRI does a lot of work, that data is really lacking. And so I think this is another opportunity, is to work with those communities, work with those countries that might actually have that data. It's just not getting into these global data sets such as GPCC, which is what I'm indicating here. So the last thing that I wanted to show, and it's just a single example, was how we can take our climate information a little bit further by actually thinking about sectoral forecasts. And I know that there are several folks on the call that are thinking a lot about sectoral forecasts or doing sectoral forecasts. So this is really geared more towards the climate-minded folks, of how useful that information really can be, and again, how important it is to have reliable but sharp information. So in this example, starting with the observations, we might know historically or in a particular month the observed climate, but we also need to, this is the country of Uruguay in Southeast South America. We also need to know something about the soil type and how much water it can hold, how deep it is, things like that. That information then can be combined in some sort of crop model, particular crop, to then indicate what is the requirements or what is the existing state for the water satisfaction, the evapotranspiration, how much water is going to run off out of a particular part of the soil, and then getting at to what extent the existing water or the predicted water is really enough for that crop. So this has been implemented in Uruguay, and it's part of a monitoring system. They have that soil data, but then it's been aggregated. They have the soil data very locally. It's been aggregated at the country level because that's the scale at which decisions are made for agriculture. And so they've brought all that information together, together with the soil type, and this is geared specifically towards pastures, not soybeans or maize, geared towards pastures. So where it's green, that means that sufficient water exists for the pasture at the time. As it starts to become yellow, that's where the pastures are becoming stressed, starting to become limiting. And where it's red, it's really very problematic. And so looking at, in this La Nina event, going into drought conditions in 2010, this monitoring really provided almost unprecedented for that country awareness of the widespread nature of drought and the impact on agriculture and the livestock in the country, which allowed then the ministers to declare emergency based on that information. So you do need to have that history so you really know what are the levels of water requirement that cause stress. You need to have those verifications on the pastures and crops. But once you have that and you have good, reliable climate information, you can bring those things together very analogously to indicate the outlooks, the future outlooks, which might help for planning or even earlier response to help potential drought-stricken parts of a country. So that's sort of a quick run through of some of the opportunities that we're facing in these areas of reliability, subseasonal, seasonal information, and sector-based forecasts. I'm going to add one more, again, that the need for complete observational data sets is really critical to doing any of this work. So these are some of the issues that I ran through. In terms of sector-based forecasts, which I'll emphasize again, having tailored climate information that needs to be reliable and merging that with other observational data can really do some amazing things. But having information on the past and the present and working towards the future, I think is an enormous opportunity to really create additional pull for this information. In the interest of opportunities in the previous talks, I'll also note that those are opportunities. The fact that this national North American multimodal ensemble is available is a huge opportunity for our research community to contribute to this type of work. The stuff that Eric was talking about, ENSO in a changing climate, is a research focus of CLIVAR, so it's another opportunity for people interested in that topic to become involved. And, IRI does a lot of this work, and we make it relevant to real people with real decisions on the ground, but we can't do this ourselves. So I'll put that out as a final opportunity that we're really interested and eager to work with others in the community that are interested in this approach to developing and using climate information. And so I would welcome you to contact us. You can contact me. Andrew Robertson is the head of the climate group, so you can contact him also. And that's it. Thank you very much.
Lisa, thanks a lot. That was really, really great, really nice, expansive discussion of the opportunities, and thanks for roping in the other presentations from this webinar. It's nice also to think about this in the context of some of the applications that you all are working on at IRI and provides products and services in many of these areas. So if there are any questions from folks on the phone, online, please raise your hand. Again, you go to the participant list and then click the hand icon, and then we'll be able to see that you have a question, and I can unmute your line. Any questions here for Lisa? Okay, I'll give it a couple seconds, Lisa. We are past noon, unfortunately, so we've
Sure.
lost a few people, but oh, we do have a question. Okay, so Julio Bachmeister has a question. Julio, I just unmuted your line. Go ahead.
Can you hear me?
Yes, we can.
Yes.
Okay, yeah, no, this is a general question, sort of out of ignorance. Has anyone looked at the impact of atmospheric model resolution, either vertical or horizontal, on the seasonal prediction problem? Is there any interest in that?
Absolutely. I think that Ben can speak to that as well, probably even better than I can. But we have a lot of GFDL people on the line as well. What I've seen so far is that it does fix some things, and I think it's extremely encouraging. I mean, the more that we're resolving processes and that we can actually get down to looking at processes, I think it's a good thing. It's always the balance, right, between costs and improvements. Maybe Ben wants to add to that.
Yeah. So the point I would add to that is the GFDL guys have the model they've submitted, the new model they've submitted to the NMME project is the floor model, and really the analysis that they've done based on a fairly robust set of hindcasts and analysis of long simulations is that increasing the resolution to something order on the 50 kilometers in the atmosphere. I don't think they changed the vertical much. The horizontal resolution to 50 kilometers, they got a big boost in performance, and they have, in fact, make the argument that that's where the investment in resolution should go instead of the ocean component. I think that might be an open question, but certainly the results there are quite compelling.
All right. Thanks.
And if any of the
GFDL...
Yeah, oh, sorry, Eric, go ahead.
Yeah, I just wanted to add on following that question on the atmosphere resolution. It helps for representing ENSO in GCMs, but clearly the physics and how you model your clouds and convection is absolutely key as well. So if you're not doing a good job with your cloud and convection, increasing the resolution is not going to help. So both have to go together, but resolution is not, you're not going to kill all the birds with that stone. So.
Okay.
If any of the GFDL participants would like to weigh in, you can use the hand raise feature. And I don't see any other questions. Julio, thanks for the question. Let's see, Ram just raised his hand, so I will unmute Ram. Ram, are you there?
Yeah, I'm there. I just wanted to add, I agree with that last comment by Eric about the need to improve the physics, and that resolution alone is not going to be the panacea. Although in our experience, it by itself has improved a lot of things. But that is sort of debatable as to whether you started from a base where resolution was guaranteed to improve some things. But ultimately, you really have to look at the physics too. One thing I would like to sort of add is, and going back to the first comment, the vertical resolution is something that is still, I would think, has not been tested enough by models in terms of pushing the models to higher vertical resolutions to see what the quality of the simulations is. I think in particular there are some features like the natural modes of oscillation which might actually improve with the higher vertical resolution, be it near the boundary layer or the tropopause or even the stratosphere. So that's, I think, still people have been increasing horizontal resolution. That's occurred in a lot of places, but very systematic tests increasing the vertical resolution along with horizontal resolution, I think, still need to get done.
Great. Yeah, thank you.
Yeah, on this specific aspect, I totally agree that again, it's the same thing that the resolution goes with the physics, but the vertical resolution goes with the horizontal resolution as well. And more specifically, for example, if you're interested in ENSO or tropical impacts at the mid-latitudes through, for example, the sudden stratospheric warmings, which provide a source of predictability from the tropics at the mid-latitudes, clearly resolving your stratosphere in a correct way is going to be important. And also I agree at the boundary layer, the coupling with the ocean, both in the ocean and the atmosphere needs to be properly resolved as well. So that's a very, very important route as well, I agree.
Leo, thanks for starting this discussion. It's an interesting discussion. Okay, so we're quite a bit past noon now. Apologies to run over so long. Thanks everybody for joining. Thank you very much to the speakers. Eric, thanks for calling in from the French countryside in the evening, and Lisa and Ben for calling in from Antipodes on the East Coast. So we have 2 webinars coming up in December. We're not going to have a webinar in November because it was shifted to early December. And the 2 topics for those are, the first one will be on marine ecosystems. It's an exploratory topic. MAPP doesn't fund any research in this area, but we're going to have some talks exploring predictions and projections of marine ecosystems. We're going to hear from Ann Holloway from the Pacific Marine Environmental Laboratory, Janet Nye from Stony Brook, and Charlie Stock from GFDL. And that'll be followed about a week later with a webinar on the topic of cloud development in the models, which is an area that MAPP does fund a number of projects in. We're going to hear from Chris Golaz from GFDL, Steve Kruger from University of Utah, and Roger Marchand from University of Washington. So I hope everybody will come back and join for those 2, and the recording of this as well as all the slides will be available on our website probably within the next 24 to 48 hours. So thanks everybody for joining. Again, thank you to the speakers for taking the time for these really very interesting and provocative presentations. Have a nice day.
Thank you.